Tonight, we're going to talk about something you already recognize the beginning of the universe. It's an idea that feels settled, a starting point, a clean line where everything begins. You've heard this before, it sounds simple, but here's what most people don't realize: the way we picture that beginning is not how the universe actually behaves. To anchor the scale immediately, consider time not as numbers, but as experience. Imagine compressing the entire history of human civilization into a single heartbeat. Not a lifetime, a heartbeat. Now imagine that heartbeat stretched until it becomes a calendar year. Human history still doesn't reach the first second of January, and even that comparison barely touches the scale we're about to enter. By the end of this documentary, we will understand what scientists actually mean when they say the beginning of the universe, why the James Webb Space Telescope has not broken physics, but has broken our intuition, and how our mental model of time itself has to change to remain usable. If you want more long-form work like this, you can subscribe. Now, let's begin. We usually imagine the universe as having a birth moment in the same way we imagine our own. There is a before, then a moment of arrival, then everything else follows. That intuition is not irrational. It comes from living in a world where almost everything we encounter has a clear beginning. A fire starts when a spark appears. A life begins at birth. A sentence begins with its first word. So when we hear the phrase the Big Bang, our intuition fills in the rest automatically. An explosion, a flash, a point in time where nothing existed, and then suddenly something did. This picture is so familiar that it rarely feels like a guess. It feels like a fact. But the Big Bang was never an explosion in space. It was not a moment where matter flew outward into emptiness. And most importantly, it was never meant to describe the absolute beginning of everything. That misunderstanding matters, because when a telescope like James Webb looks deep into the universe and sees structures that appear too old, too organized, or too early, the problem is not that the universe is misbehaving. The problem is that our starting intuition was never correct to begin with. To see why, we have to slow down and strip the idea back to something much smaller and more manageable. When astronomers talk about looking far away, they are not talking about distance in the everyday sense. They are talking about time. Light does not arrive instantly. It moves at a fixed speed, and that speed, while unimaginably fast, is still slow on cosmic scales. So when we look at the sun, we see it as it was about 8 minutes ago. That delay is already real, but it's small enough that we can ignore it. When we look at the nearest stars, we see them as they were years ago. When we look at distant galaxies, we are looking billions of years into the past. This is not a metaphor. It is not a visualization trick. It is a physical delay built into the structure of reality. Now let's stretch that idea gently. Imagine watching a city skyline through a thick fog, where the fog delays light unevenly. The farther away a building is, the more out of date the image becomes. Near buildings look current. Distant buildings show old estates. Some lights are still on that have already been turned off. Some windows are dark that are now lit. The universe works like this, except the fog is simply distance, and the delays are not minutes or hours, but billions of years. James Webb was designed to see through this delay more clearly than any instrument before it, not by seeing farther in space, but by detecting older light that has been stretched, cooled, and shifted as the universe expanded while it travelled. This matters because the early universe was not transparent. In its earliest phases, it was filled with hot plasma that scattered light in every direction. Photons could not travel freely. The universe was opaque, like a dense fog you could not see through at all. Only after hundreds of thousands of years did that fog clear enough for light to move long distances. That moment, the release of the oldest light we can directly observe, is often confused with the beginning itself. It is not the beginning. It is the earliest surviving photograph. Even that photograph is incomplete. It shows temperature variations, not structures. It tells us about density, not galaxies, and it represents a universe already old by human standards. So when we say we can't see before the Big Bang, what we really mean is something much more specific. Our current observational tools cannot access information from earlier phases because the universe itself was not yet transparent to light. This distinction is critical because it changes the meaning of before. Before in everyday language assumes a timeline that already exists, but time itself is part of the system we are describing. It is not an external container the universe sits inside. It is woven into the same structure as space, matter, and energy. That realization didn't come easily. For most of human history, time was treated as absolute. It flowed the same everywhere, independent of motion, gravity, or observation. That assumption worked well enough for building houses, navigating oceans, and predicting eclipses. It failed when we pushed the scale. When Einstein introduced relativity, time stopped being universal. It became local, dependent, flexible under extreme conditions. Two observers could disagree about the duration between the same events and both be correct. This wasn't philosophy, it was measurement. Clocks on fast-moving satellites tick at different rates than clocks on Earth. Without correcting for this, GPS would fail within minutes. The effect is small, but it is real, measurable, and unavoidable. Now extend that same logic to the entire universe. If time is part of the universe, then asking what happened before the universe becomes a category error, like asking what is north of the North Pole. The question uses familiar language, but the structure it assumes no longer exists. That doesn't mean nothing happened. It means our everyday intuition about temporal ordering is no longer reliable. Cosmology deals with models, mathematical frameworks that describe how the universe evolves under certain assumptions. The Big Bang model describes an expanding universe that was once hotter, denser, and more uniform than it is now. It does not describe creation from nothing. It does not claim to explain the absolute origin of reality. It simply runs the equations backward until they stop working. When we do that, densities increase, temperatures rise, space itself shrinks. Eventually, the equations reach a point where known physics can no longer describe conditions accurately. That point is often labelled the Big Bang, but it is not an event we understand. It is a boundary in our knowledge. This is where intuition tends to collapse. We are used to boundaries marking real edges, a wall, a shoreline, a deadline. But in science, boundaries often mark the limits of models, not the limits of reality. James Webb did not suddenly look past that boundary. It did not see before time. What it did was something subtler and more disruptive to intuition. It showed that complex structures formed earlier than our simplified timelines expected. Galaxies that look mature, stars that appear organized, chemical elements that imply multiple generations of stellar activity, all appearing when the universe was supposedly too young for such complexity. This does not mean the universe is older than itself. It means our intuitive picture of how fast structure should emerge was incomplete. We assumed smoothness, gradual build-up, a slow, orderly progression from simplicity to complexity. That assumption felt reasonable because it matches many processes we see locally. But the early universe was not local, it was extreme. Small differences in density were amplified by gravity. Regions slightly heavier pulled in more matter, becoming heavier still. This feedback loop operates relentlessly. Over vast scales and long durations, tiny variations become dominant structures. This is not a flaw in the Big Bang model. It is a feature that requires careful modelling and immense computational effort to track accurately. James Webb is not rewriting the beginning of time. It is forcing us to confront how fragile our intuition becomes when we compress billions of years into a mental snapshot. What feels too early to us is not early to a universe governed by exponential growth, nonlinear feedback, and expanding space-time. At this point, we can pause and take inventory of what we now understand. The Big Bang is not an explosion. It is not a moment of creation from nothing. It is a model describing an early, hot, dense phase of an expanding universe. Time is not a backdrop, it is part of the system. Observations are not direct views of the past, they are delayed signals filtered through the physics of light and expansion. And when new instruments reveal unexpected structure, the failure is not in reality behaving incorrectly, it is in our simplified expectations. This framework will matter as we continue, because the phrase older than the Big Bang only makes sense if the Big Bang is misunderstood as an absolute starting line. Once that intuition is dismantled, the apparent paradox dissolves not into mystery, but into a more precise, more constrained, and more stable understanding of what we can and cannot currently know. Once that intuition loosens, something else becomes visible. The problem was never that the universe is hiding its past. The problem is that we were listening with the wrong senses. Human perception evolved to track motion, colour, and change across very narrow ranges. We see a thin slice of light. We feel time passing at a steady pace. We experience distance through effort and delay. None of these instincts scale well. They fail quietly, without warning, long before we notice. Light, in particular, behaves in a way that feels familiar only at short distances. A lamp turns on, a room brightens instantly. At that scale, the speed of light might as well be infinite, but it is not. And once we leave the room, leave the city, leave the planet, its finite speed stops being a detail and becomes the dominant feature. Every photon James Webb detects has a history, not a metaphorical one, a physical trajectory through expanding space. As the universe stretches, the wavelength of that light stretches with it. Blue light slides toward red. Red light slides beyond visibility, into infrared. This is not a Doppler effect from motion through space. It is space itself changing while the light is in transit. This distinction matters because it breaks another quiet assumption, that light preserves its identity as it travels. It does not. Its energy changes, its wavelength changes, its informational content survives, but only if we know how to decode it. For decades, our telescopes were blind to much of this stretched light. They were optimized for what human eyes evolved to see. James Webb was not built to match human vision. It was built to catch photons that have been travelling so long that the universe has reshaped them. This is why Webb operates primarily in the infrared, not because the early universe was dim, but because it has been reddened by time itself. Now slow this down. Imagine a sound wave travelling through air while the air is expanding. The pitch would drop continuously, not because the source changed, but because the medium did. By the time it reached you, it would no longer sound like the original note. Light behaves the same way, except the expansion never stops. When Webb measures the spectrum of a distant galaxy, it is not just seeing light, it is measuring how much the universe has expanded since that light was emitted. That expansion factor becomes a clock. But clocks only work if you understand what they are measuring. Redshift does not tell us age directly, it tells us relative expansion. To turn that into time, we need a model of how fast the universe has expanded at different epochs. That model is built from many inputs: cosmic background radiation, supernova distances, galaxy distributions, and the behavior of gravity on large scales. This is where intuition often reaches for certainty that does not exist. We tend to imagine cosmic age as a simple subtraction problem. Light left a galaxy X billion years ago, therefore the galaxy is X billion years old. But that assumes the galaxy formed at the same moment it emitted that light. It assumes no prior history. It assumes simplicity where none is guaranteed. Galaxies are not single events, they are processes. Stars form, die, and recycle material, gas collapses, fragments, and ignites. Structures merge, distort, and reorganize. When Webb sees a galaxy that appears mature, what it is actually seeing is evidence of prior cycles that must have occurred even earlier. This is not a contradiction, it is a compression problem. We are taking billions of years of activity and collapsing them into a single image. When that image looks too structured, the discomfort we feel is not a scientific alarm, it is a cognitive one. To handle this, cosmology separates three things that intuition tends to blend together: observation, inference, and modelling. Observation is the detection of photons, their wavelengths, intensities, and distributions. This is the raw data. It is constrained by instrument sensitivity and physical law. Inference is what we extract from that data using known physics, elemental abundances, star formation rates, mass estimates. These are not guesses, but they are conditional. Modelling is where timelines appear. Models integrate inferences across large scales to reconstruct histories. They are powerful, but they are not reality itself. When headlines say "older than the Big Bang," they're collapsing all three layers into a single phrase. The phrase feels dramatic because it violates a simplified model that was never the full story. What Webb is actually doing is tightening constraints. It is forcing models to account for faster structure formation, earlier star birth, and more efficient matter aggregation than some earlier simulations assumed. That adjustment is not unprecedented. It is expected whenever measurement resolution increases. This has happened before. When the first telescopes revealed that the Milky Way was not the entire universe, but one galaxy among many, the shock was not that the universe changed, it was that our map did. When cosmic expansion was discovered, the shock was not motion but scale. Distances that had been treated as static were suddenly dynamic. Each time, intuition resisted not because the data was unclear, but because the mental compression failed. Now consider time again, but differently. We often think of age as a property objects possess, like weight or colour, but cosmic age is relational. A galaxy does not carry a timestamp. Its age is reconstructed from physical states that themselves depend on environment and history. Two galaxies observed at the same redshift can have very different formation histories. One may have formed stars rapidly and early, another slowly and later. Both exist at the same cosmic time, but their internal clocks differ. This is already true on small scales. Two people the same age can have vastly different life histories. We accept this easily because we're used to variation. On cosmic scales, we unconsciously expect uniformity. That expectation has no physical basis. The early universe was not a smooth canvas. It was a turbulent medium with regions evolving at different rates. Gravity does not wait for global permission. It acts locally, relentlessly, wherever density allows. So when Webb sees chemical elements that require multiple generations of stars, the implication is not that time ran backward. It is that some regions progressed faster than average. Again, the word average hides complexity. Cosmic timelines are statistical constructs. They describe trends, not guarantees. When we say galaxies formed around this time, we are summarizing distributions, not issuing schedules. James Webb is sampling the tail ends of those distributions, the earliest, densest, fastest evolving regions. These were always allowed by physics. They were just difficult to observe. At this point, another intuition tends to surface the idea that there must be a single, definitive age for the universe that everything respects. This idea is emotionally comforting. It suggests a synchronized origin. But synchronization is rare in physics. Even in systems with well-defined starting conditions, local variation emerges quickly. Think of a cooling surface. It begins at uniform temperature. Tiny fluctuations grow, patterns form, regions diverge. The start was shared, but the evolution was not identical. The universe behaves similarly, except the surface is space-time itself, and the cooling spans billions of years. So when we say the universe is approximately 13.8 billion years old, we are not marking a birthday. we are describing a parameter within a model that fits current observations with known uncertainties. That number is stable, but not sacred. It is refined, not revered. James Webb does not threaten that stability. It operates within it. What it threatens is the casual way we collapse deep time into tidy narratives, the idea that complexity must wait its turn, the assumption that early automatically means simple. Those assumptions were always conveniences. Now let's pause again and rest what we've rebuilt. We understand that light carries time information through redshift. We understand that age is inferred, not observed. We understand that galaxies are processes, not points. We understand that models describe averages, not absolutes. And we understand that faster than expected evolution is not a paradox, but a correction. This prepares us for the next pressure point, where intuition often tries to reassert itself the question of limits. Not observational limits, but conceptual ones, where physics itself stops giving clear answers not because of mystery, but because of structure. That boundary is not where headlines place it, and it is not where the phrase before the Big Bang suggests. It lies somewhere quieter, deeper, and more precise. As intuition stretches further, it eventually reaches a place where adding more detail no longer helps, not because reality ends, but because the tools we're using stop applying cleanly. Physics has boundaries that are not walls. They are regions where our equations lose reliability. This distinction matters, because when we approach those regions, language tends to harden into absolutes that the science itself does not claim. The earliest moments of the universe sit inside one of these regions. If we continue running our current models backward compressing space, raising temperature, increasing density, we reach a regime where gravity and quantum mechanics both matter at the same time. That combination is rare in nature. On human scales, gravity is negligible. On subatomic scales, it is irrelevant. Only under extreme compression do the two become inseparable. Our theories were not built for that overlap. General relativity describes gravity as the curvature of space-time. It works extraordinarily well for stars, galaxies, and the expansion of the universe as a whole. Quantum mechanics describes particles, fields, and interactions at microscopic scales. It works extraordinarily well for atoms, radiation, and fundamental forces. Each theory has been tested to remarkable precision in its own domain. But when densities approach what we call the Planck scale, those domains collide. Space-time itself becomes subject to quantum uncertainty. The smooth geometry assumed by relativity may no longer exist. Distances, durations, and even causal order may fluctuate. This is not speculation layered on ignorance. It is the direct consequence of extending well-tested equations beyond the conditions where they have been validated. At this point, something important happens to intuition. We tend to imagine unknown regions as blank spaces, waiting to be filled with future discoveries. But in physics, unknown often means ill-defined. It is not that we lack data, it is that the concepts themselves stop behaving coherently. Time is one of those concepts. In everyday experience, time is continuous. It flows smoothly. We divide it into seconds and hours, but we assume the underlying flow is uniform. That assumption works because, at our scale, it is effectively true. Near the Planck regime, that assumption may fail. Time may not be a continuous parameter at all, or it may exist, but not in a way that supports a global ordering of events. This is where phrases like before the Big Bang become unstable, not forbidden, just undefined. If time itself emerges from deeper structure, then asking what happened before time is not meaningful in the way the sentence suggests. It is like asking what temperature was doing before matter existed. The grammar is familiar, the reference frame is not. Cosmology does not hide this limitation, it marks it carefully. When scientists say that our models break down near the Big Bang, they are not conceding defeat, they are reporting a boundary condition, a place where extrapolation stops being trustworthy. James Webb does not cross that boundary. No telescope can. That boundary is not about distance or sensitivity. It is about the internal consistency of our descriptions. What Webb does instead is tighten the approach. It tells us how close we can get while staying within well-defined physics. This is why claims about detecting something older than the Big Bang require careful translation. Webb detects light emitted at very high redshift. From that light, we infer properties of galaxies at early cosmic times. Those inferences rely on models of stellar evolution, chemical enrichment, and gravitational collapse models that operate comfortably away from the Planck regime. Nothing in those observations requires physics beyond the Big Bang model. They require refinement within it. The confusion arises when we imagine the Big Bang as a sharp temporal edge rather than as a regime transition. Our language encourages this. Bang suggests an event, but the mathematics describes a limit. As we approach that limit, certain quantities diverge. Density increases without bound. Temperature rises beyond known scales. Space-time curvature intensifies. In mathematics, divergences often signal that a description is incomplete, not that reality is infinite. They tell us where new variables, new frameworks, or new principles are needed. Historically, this has happened before. Classical physics predicted infinite energy output from blackbody radiation. That divergence was resolved by quantization. Newtonian gravity predicted singularities at point masses. That divergence was softened by relativity. Each time, the failure was not in nature but in the model's domain of validity. The Big Bang singularity plays a similar role. It marks the edge of applicability, not the origin of existence. This is where speculative theories enter not as answers, but as attempts to build continuity. Inflation is one such attempt. It proposes a brief period of extremely rapid expansion early in cosmic history. This expansion smooths irregularities, explains observed uniformity, and seeds structure through quantum fluctuations stretched to cosmic scales. Inflation is not directly observed. It is inferred from patterns in the cosmic background radiation and large-scale structure. It is a model that solves specific problems efficiently. Other proposals go further. Some suggest cyclic universes, where expansion follows contraction. Others suggest quantum bounces replacing singularities. Some explore higher dimensional frameworks or emergent spacetime. What all of these share is restraint. They do not claim to describe before in an everyday sense. They attempt to extend physical description beyond a boundary while respecting known constraints. And they remain provisional. This restraint is often lost in translation. The public hears about bold ideas and assumes certainty. Scientists hear about careful extensions and emphasize uncertainty. Neither reaction is wrong. They operate at different layers. To maintain stability, we have to keep those layers separate. Observation, Webb sees light, inference that light implies early structure formation. Modeling, some timelines adjust. Speculation physics near the earliest regimes may require new frameworks. Unknowns. The nature of those frameworks is not settled. This separation prevents confusion from turning into contradiction. At this depth, intuition often tries to simplify again by reaching for absolutes. Either we know, or we don't. Either the universe had a beginning, or it didn't. Either time exists, or it doesn't. Reality is rarely so binary. We can know how far our models reach. We can know where they stop. We can know why they stop. That knowledge is stable even when answers are not. So when we hear that something appears older than the Big Bang, the correct response is not disbelief or excitement, it is translation. What is actually being challenged is not the age of the universe, but the compression of early cosmic history into overly rigid expectations. The universe does not owe us neat milestones. It evolves according to local conditions amplified across scale. Some regions ignite early, some remain diffuse longer, some structures form rapidly, others take time. This diversity is not noise, it is the signal. James Webb is revealing that diversity earlier than before. It is showing us that the early universe was not a quiet waiting room. It was active, uneven, and efficient at building complexity where conditions allowed. Nothing about this requires rewriting the foundational model. It requires loosening our grip on simplified narratives. Now we can rest again inside what we've rebuilt. We understand that there is a boundary where current physics loses definition. We understand that this boundary is not an event in time, but a limit of description. We understand that speculation exists beyond it, carefully constrained. We understand that Webb operates well within known physics, refining early timelines rather than overturning them. And we understand that apparent paradoxes dissolve when observation, inference, and modelling are kept distinct. This prepares us for the next shift, where scale alone is no longer enough, where we must confront not just how early structures formed, but why our expectations about formation speed felt so natural and why they were misleading. The expectation that complexity must take time feels almost instinctive. We associate order with patience, construction with duration, and maturity with age. This intuition is reinforced everywhere we look. Mountains erode slowly. Ecosystems develop over generations. Technologies evolve through iteration. So when early galaxies appear structured, massive, and chemically evolved, the discomfort is not technical, it is psychological. Something feels rushed. To understand why that feeling misleads us, we have to examine what slow actually means in a universe governed by gravity, abundance, and scale. Gravity does not wait. It does not negotiate. It acts continuously, everywhere, on everything with mass or energy. Its apparent gentleness in daily life is not a property of the force itself, but of the conditions we live in. Low densities, small masses, large separations. The early universe had none of these. Matter was packed far more tightly than it is now. Distances were shorter, densities were higher. Under those conditions, gravitational collapse accelerates dramatically. This is not an abstract claim. It follows directly from the equations. The timescale for collapse depends on density. Increase the density, and the collapse time shrinks. Double the density, and the timescale drops by more than half. Now repeat that increase not twice, but thousands of times. Regions of the early universe that were just slightly denser than average became gravitational sinks. Matter flowed toward them. As they gained mass, their pull strengthened. As their pull strengthened, they gained more mass. This is a feedback loop that does not require coordination or delay. From our perspective, this looks like rapid organization. From the universe's perspective, it is simply gravity doing what it always does, under conditions we no longer experience. Another intuition quietly interferes here, the idea that early means primitive. We unconsciously associate youth with simplicity because that is how biological development works. Embryos are simpler than adults. Early civilizations have fewer tools. But cosmic evolution is not biological. It does not optimize gradually through trial and error. It unfolds according to initial conditions amplified by deterministic laws. In some regimes, that amplification is extremely efficient. The first stars, for example, did not resemble the Sun. They were larger, hotter, and shorter-lived, formed from pristine hydrogen and helium. They burned through their fuel rapidly and ended their lives in violent explosions. Those explosions enriched surrounding gas with heavier elements, carbon, oxygen, iron on timescales far shorter than anything in human history. A single massive star could alter its environment profoundly in a few million years. A few million years sounds long until we anchor it properly. If we compress the entire age of the universe into 1 year, the first stars form within the first day. Their deaths occur before the first week ends. Entire cycles of stellar birth and destruction complete, while the cosmic calendar is still in January. This compression is not a trick. It reflects how front-loaded cosmic activity can be under high-density conditions. James Webb is sensitive to the infrared glow of stars and galaxies during this early, active period. It is detecting systems that have already undergone multiple rapid cycles. To our intuition, they look too mature. To gravity, they are simply efficient. Another hidden assumption adds to the confusion the belief that galaxies must assemble piece by piece, slowly accreting matter over long periods. While this does happen, it is not the only pathway. In dense environments, collapse can be coherent. Large regions fall inward together. Fragmentation occurs inside collapsing clouds, forming stars in bursts rather than drips. This process is violent, chaotic, and fast. Simulations that include these effects, high initial densities, efficient cooling, strong feedback produce early galaxies that look remarkably like what Webb observes. The mismatch arises when simplified models underestimate just how extreme early conditions were. Again, this is not a failure of physics, it is a failure of conservative expectation. Our intuition prefers linearity, it expects proportionality, twice the time, twice the result. Gravity does not operate that way, it compounds. Once a structure crosses a threshold, growth accelerates. Before that threshold, little appears to happen. This creates the illusion of sudden emergence, when in fact the process was continuous but non-linear. Think of condensation forming on a surface. For a long time, nothing seems to change. Then droplets appear rapidly. The underlying process was always active, but perception lags until a threshold is crossed. Early galaxies cross many thresholds quickly. Cooling allows gas to collapse. Collapse triggers star formation. Stars generate radiation and explosions. Feedback reshapes surrounding matter. New stars form in enriched environments. Structure compounds upon structure. All of this can occur in a few 100 million years, a blink on cosmic timescales. So when Webb reveals galaxies at redshifts that correspond to very early epochs, the surprise is not that they exist. The surprise is that our mental timelines were too cautious. This is where historical context helps. Early cosmological models were intentionally simple. They assumed smoothness because complexity was computationally intractable. They averaged over variation because resolution was limited. These choices were pragmatic, not principled. As data improves, those simplifications are relaxed. Variance becomes visible. Extremes matter. James Webb does not replace earlier telescopes. It complements them by probing a regime that was previously inaccessible. It fills in the early part of distributions that were always expected to have tails. The language of too early comes from mistaking the average for the limit. At this point, we can stabilize another piece of understanding. We understand that gravitational collapse accelerates under high density. We understand that early cosmic conditions were extreme. We understand that nonlinear processes compress timelines. We understand that complexity does not require patience, only the right conditions. And we understand that early galaxies appearing mature is a reflection of efficiency, not anomaly. This realization prepares us for a subtler shift. Even if early structure formation is fast, there remains a question that intuition clings to coordination. How did regions so far apart appear so similar? How did order emerge without communication? Why does the universe look uniform at large scales if evolution is local and uneven? That question is not answered by speed alone. It requires another conceptual adjustment, one that reshapes how we think about expansion, causality, and shared history. The sense that the universe is coordinated comes from looking at it after the fact. We see large-scale uniformity and instinctively imagine a process that enforced it, some guiding mechanism, some long-range communication. But coordination is not always the result of interaction. Sometimes it is the result of shared origin. To understand this, we have to return to expansion not as motion, but as geometry. When we say the universe is expanding, we often picture galaxies flying away from each other through space. That image is serviceable at small scales, but it breaks at large ones. What is expanding is not the contents of space, but space itself. Distances between points increase even if those points are not moving locally. This expansion stretches everything embedded within it, wavelengths of light, separations between galaxies, and the causal horizons that limit interaction. Early in cosmic history, those horizons were much smaller. Regions that are now far apart were once close enough to share conditions, exchange energy, and equilibrate. This matters because it reframes the uniformity we observe today. The cosmic microwave background, the oldest light we can see, is remarkably uniform in temperature across the sky. Tiny variations exist, but they are small. Without context, this looks puzzling. How did distant regions know to match? The answer is not that they communicated later. It is that they were once the same region. Inflation provides a mechanism for this. It proposes that a very small, causally connected patch of space underwent rapid expansion, stretching it far beyond the size of the observable universe. Regions that now appear disconnected were once neighbours. This does not require fine-tuning. It requires an early phase with specific properties, high energy density, and a particular field behaviour. Those properties are not arbitrary. They arise naturally in many high-energy theories. Inflation is not directly observed, but it leaves fingerprints. The uniformity of the background radiation, the specific spectrum of density fluctuations, the absence of certain large-scale irregularities. These fingerprints match observations with striking precision. Now slow this down again. Imagine a balloon with a tiny pattern drawn on it. Inflate the balloon rapidly. The pattern stretches. Points that were millimeters apart are now meters apart. They did not coordinate after inflation. Their similarity is inherited. The analogy ends there, we discard it. The important point is inheritance, not communication. Once inflation ends, expansion continues at slower pace. Structures form locally, driven by gravity, but the large-scale uniformity remains because it was imprinted early, before regions separated beyond causal contact. This helps resolve another intuition failure, the idea that early complexity and large-scale smoothness are in tension. They are not. They operate at different scales. Small-scale variation grows from tiny fluctuations. Large-scale uniformity persists because those fluctuations were small relative to the whole. James Webb probes the small-scale end of this picture. It sees galaxies forming in the valleys of the early density landscape. It does not challenge the smoothness of the background. It reveals how structure rides on top of it. This separation of scales is easy to miss because our experience rarely spans orders of magnitude cleanly. In everyday life, local and global behaviours often blur. In cosmology, they decouple. Another intuition quietly dissolves here, the expectation that causality must be obvious. We are used to seeing causes precede effects within clear boundaries. Push a glass, it falls. Heat water, it boils. These processes are local and immediate. Cosmic causality is extended and layered. Some causes act early and globally, others act later and locally. Their effects coexist in the final picture. So when we see early galaxies embedded in a uniform universe, we are not seeing contradiction. We are seeing the superposition of processes operating at different times and scales. This also clarifies why older than the Big Bang language misfires. Uniformity, structure, and complexity do not require time travel. They require appropriate initial conditions and lawful evolution. Those conditions were set when the universe was young, dense, and connected. From there, everything else follows. At this depth, another stabilization point emerges. We understand that expansion stretches space, not objects through space. We understand that early regions were once connected. We understand that large-scale uniformity is inherited, not enforced. We understand that local complexity grows within a globally smooth background, and we understand that Webb's observations fit within this layered causality. This layered view also explains why cosmology often speaks in averages and perturbations rather than specific histories. The background sets the stage, fluctuations write the details. Now, one more intuition tends to surface before it fully lets go the belief that explanation must eventually arrive at a single cause, one origin, one moment, one mechanism. But the universe does not operate that way. It unfolds through overlapping phases, each setting constraints for the next. No single phase explains everything, each explains why the next is possible. This is not a weakness, it is a structural property of complex systems. So as we continue, we will not be looking for a deeper before. We will be examining how successive layers of description become necessary as scale increases, and why insisting on a single ultimate explanation creates confusion rather than clarity. As the layers stack, something subtle happens to our sense of explanation. We begin to notice that each layer answers a different kind of question, and that forcing them to answer the same one creates friction that feels like mystery. One layer tells us how the universe expands, another tells us how matter clusters, another tells us how stars ignite and die. None of these layers is optional, none replaces the others, they interlock. The confusion around older than the Big Bang often comes from skipping this interlocking and asking one layer to do all the work. So let's slow down and isolate one of the most easily overlooked layers, the difference between age and sequence. In everyday language, age implies order. Something older comes first, something younger comes later. This works because we live inside systems where clocks are synchronized and histories are short. Cosmic history is not synchronized that way. The universe does not provide a single global clock that every process obeys identically. It provides a set of physical laws that operate locally under changing conditions. From those laws, sequences emerge but not uniform schedules. This is why cosmology rarely speaks in exact dates. It speaks in eras, transitions, and regimes. Radiation dominated, matter dominated, dark energy dominated. These are not calendar entries. They are descriptions of what physics mattered most at different stages. Within each regime, countless processes unfolded at different rates. Some stars formed early and burned out quickly. Others formed later and persist. Some galaxies assembled rapidly in dense knots. Others grew slowly in isolation. Age, in this context, is not a single axis. It is a family of overlapping timelines. James Webb does not assign birthdays. It reveals states. From those states, we infer plausible sequences, but always with branching possibilities. This is why the phrase "this galaxy is older than expected" needs careful unpacking. Older than what expectation based on which assumed sequence? Under what environmental conditions? Often, the expectation being violated is not a physical law, but a simplified narrative that assumed homogeneity where there was none. Another intuition quietly interferes here, the idea that early conditions must be fragile, that complexity emerging early would be easily disrupted or erased. In fact, early conditions can be robust precisely because everything is dense and energetic. Feedback loops are strong. Structures that form can stabilize quickly, locking in configurations that persist. Consider star clusters forming inside collapsing clouds. Once stars ignite, their radiation and winds reshape the environment, halting further collapse in some regions while triggering it in others. This feedback does not undo structure, it organizes it. Early galaxies experience intense versions of this process. Their internal dynamics settle rapidly, not because time is abundant, but because energy flows are extreme. This robustness explains why Webb sees coherent systems rather than amorphous chaos. Early does not mean delicate. Often, it means decisive. Now consider the role of dark matter. Dark matter does not interact with light, but it interacts gravitationally. It forms scaffolding long before ordinary matter can cool and collapse. This scaffolding guides where galaxies form and how they grow. Dark matter structures begin forming early, very early, because they are not slowed by radiation pressure or atomic processes. They clump as soon as gravity can act effectively. By the time ordinary matter begins forming stars, much of the large-scale structure is already outlined. Galaxies do not appear randomly. They condense within pre-existing gravitational wells. This further compresses timelines. What looks like sudden organization is actually the visible phase of a longer, invisible preparation. James Webb sees the visible phase. It sees stars and dust and gas glowing in infrared light. It does not see the dark matter halos that shape those systems, but those halos were there first. Again, intuition lags because it tracks what is visible, not what is influential. At this point, we can rest another piece of understanding. We understand that cosmic age is not a single synchronized clock. We understand that sequences overlap rather than align. We understand that early structures can be robust, not fragile. We understand that dark matter accelerates visible formation by pre-shaping space, and we understand that Webb reveals outcomes, not entire histories. This layered view also explains why scientific confidence can coexist with open questions. Knowing how a process operates does not require knowing every initial detail. It requires knowing the constraints that shape outcomes. In cosmology, those constraints are strong. Expansion rate limits interaction, gravity amplifies density, thermodynamics governs cooling, nuclear physics dictates stellar life cycles. Within these constraints, variation is expected but not arbitrary. So when observations fall within allowed ranges, even if they sit at the extremes, they reinforce the framework rather than undermine it. The remaining discomfort comes from language. Words like beginning, origin, and before carry everyday meanings that no longer apply cleanly at cosmic scale. We use them anyway, because abandoning them entirely would leave us unable to speak at all. But precision requires constant translation. The Big Bang is not a birthday, age is not a timestamp, early is not simple. Once those translations are internalized, the apparent paradox dissolves into a more stable picture. Now, one more intuition waits to be addressed before we go deeper. It concerns detection itself. There is a quiet assumption that seeing farther automatically means seeing earlier, that more powerful instruments reveal deeper truths simply by extending reach. This is only partially true. Detection is shaped by selection effects, biases, and thresholds. What we see first is not necessarily what formed first, it is what is easiest to detect under given conditions. Understanding this will further stabilize how we interpret Webb's discoveries and why older than the Big Bang headlines are not just misleading, but structurally incorrect. Seeing is never neutral. Every instrument filters reality before it reaches us. This is true for eyes, microscopes, and telescopes alike. What changes with scale is not whether filtering happens, but how strongly it shapes interpretation. James Webb does not show us the early universe as it was in full. It shows us the parts of it that can announce themselves across immense distances, through expanding space and into a very specific set of detectors. This matters because detection favours extremes. Bright objects are easier to see than faint ones. Massive systems are easier to detect than small ones. Rapid star formation outshines slow accumulation. These biases are not flaws. They are unavoidable consequences of physics. When Webb looks deep into cosmic time, it is not sampling the early universe evenly. It is catching the loudest signals, the galaxies that formed stars aggressively, the regions where matter collapsed efficiently, the systems that lit up quickly. Quiet histories remain invisible. This creates a powerful illusion that the early universe was dominated by advanced structures. In reality, we are seeing the upper envelope of what was possible, not the median experience. To anchor this intuition, imagine standing on a dark coastline at night, watching distant ships. You do not see every vessel, you see the ones with the brightest lights. From that limited view, it would be easy to conclude that all ships are large and illuminated. The smaller, dimmer boats still exist. They simply do not announce themselves across distance. The analogy ends here. The early universe contained a wide range of environments. Some regions collapsed early and violently. Others remained diffuse for much longer. Webb preferentially detects the former. This selection effect becomes more pronounced the farther back we look. Early times compress observational windows. Only the most energetic processes can overcome distance, redshift, and attenuation. So when Webb finds galaxies that appear massive and evolved very early, it is not revealing the typical case, it is revealing the detectable case. This distinction stabilizes another intuition that tends to wobble the idea that observation equals census. Astronomy is not a complete inventory. It is a constrained sampling problem. Every detection sits inside a funnel shaped by physics, technology, and time. Understanding this prevents overinterpretation. It also explains why new instruments often appear to break existing models. They are not changing reality. They are accessing different slices of the distribution. Earlier telescopes were sensitive to ultraviolet and visible light. They saw later hotter stars and nearer galaxies. Webb sees infrared. It opens a window to dust-obscured regions and stretched early light. That window overlaps partially with previous ones, but it also extends into new territory. Where overlap exists, consistency is checked. Where extension occurs, expectations must be recalibrated. This is not a crisis. It is how empirical science evolves. Another quiet intuition dissolves here, the belief that earlier detection implies earlier formation. Seeing a galaxy at high redshift does not mean it formed exactly at that moment. It means that is when it emitted the light we detect. Its formation history could extend significantly earlier. So when a galaxy appears chemically enriched or structurally organized, the implication is not that everything happened instantaneously. It is that its prior history is compressed into a short observational baseline. Compression magnifies surprise. This is especially true when time intervals shrink. The difference between 200 million and 400 million years feels small numerically, experientially, both are beyond everyday intuition. But physically, doubling time in a regime of rapid evolution can mean multiple generations of stars. Again, repetition matters. Early times are dense. Dense conditions accelerate processes. Accelerated processes compress histories. Compressed histories look abrupt. Abruptness triggers intuition failure. Once this loop is internalized, the shock fades. Another factor quietly shapes what we see: cosmic variance. The observable universe is large, but it is not infinite. When we look at small patches of sky deeply, we are sampling specific regions that may not be representative. Some areas are richer, some are emptier, some host unusually early structures. James Webb's deep fields are extraordinary views, but they are not averages. They are selected windows. As more observations accumulate, distributions will fill in. Extremes will be contextualized. What now feels anomalous will settle into place. This has happened repeatedly in astronomy. Early discoveries always feel exceptional. Later, they become part of a continuum. At this point, we can pause and rest again. We understand that detection favors bright, massive, active systems. We understand that early observations sample extremes, not norms. We understand that seeing early does not mean forming instantly. We understand that Webb opens a new observational window with its own biases, and we understand that headlines often mistake selection effects for paradoxes. With this in place, another intuition is ready to be addressed, one that sits even deeper. It is the intuition that reality must be revealed in chronological order, that we should first understand the beginning, then the middle, then the present. The universe does not reveal itself that way. We reconstruct its history backward, from consequences to causes, from remnants to origins. This inversion is unavoidable, and it shapes how certainty accumulates. Understanding this inversion is essential to remaining stable as scales continue to grow and explanations become less intuitive. We never observe beginnings directly, we infer them. This is not a limitation unique to cosmology. It is how all historical sciences operate. Geology reconstructs Earth's past from rock layers. Biology reconstructs evolution from fossils and genomes. None of these fields witnesses origins. They work backward from traces. Cosmology does the same, but with a crucial difference: the traces themselves are altered by the expansion of the universe. Distance does not just separate cause from effect, it transforms the signal. So reconstruction in cosmology is not simply backward reasoning, it is backward reasoning through a deforming medium. This inversion quietly undermines another intuition, that explanation proceeds from first cause to final state. In practice, it proceeds in the opposite direction. We start with what exists now, we measure its properties, we infer what conditions must have preceded it. Then we check whether those inferred conditions are consistent across independent lines of evidence. This is why cosmology places so much weight on consistency rather than direct proof. No single observation establishes a beginning. Multiple independent observations converge on a shared history. The cosmic background radiation, for example, is not evidence of a single event. It is evidence of a phase transition, a time when the universe cooled enough for light to travel freely. That interpretation only holds because it matches predictions from expansion, thermodynamics, and atomic physics simultaneously. James Webb fits into this structure as another consistency check, not a revelation of origin, but a refinement of early conditions. This backward reconstruction explains why cosmology can be confident about broad features while remaining agnostic about details. We know the universe expanded from a hotter, denser state because many lines of evidence converge on that conclusion. We do not know the exact microphysics of the earliest moments because fewer constraints reach that far. This asymmetry is stable, it does not signal failure. But intuition resists it, because we are used to forward causation. We plan by imagining future outcomes. We remember by recalling past events. Reconstructing an unseen origin from present remnants feels indirect, even suspicious. Yet it is the only option available at this scale. Now consider how this affects the phrase older than the Big Bang. If the Big Bang is understood as a reconstructed regime, a set of inferred conditions, then nothing can be observed as older than it in a literal sense. Observations inform the reconstruction. They do not sit outside it. When Webb reveals early galaxies, those observations feed back into the reconstruction. They do not stand in opposition to it. The model adjusts to accommodate new constraints, just as it always has. The apparent conflict arises only if we treat the Big Bang as a fixed narrative rather than a flexible framework. Frameworks are not stories, they are scaffolds. They hold explanations in place while remaining adjustable. This brings us to another intuition that needs careful dismantling: the expectation that scientific explanations converge toward a final, complete picture. In everyday problem solving, completeness is achievable. A puzzle has a solution. A machine has a blueprint. Once assembled, uncertainty vanishes. In cosmology, completeness is asymptotic. Explanations improve, narrow, and stabilize, but they do not close. This is not because the universe is mysterious by nature. It is because access to information is fundamentally limited by causality and expansion. Some signals will never reach us. Some regimes will never be directly sampled. Recognizing this is not defeat, it is calibration. James Webb does not promise final answers, it promises better constraints. Each constraint reduces the range of plausible histories. Over time, that range narrows. The Big Bang model itself emerged this way. It replaced static universe models not because it explained everything, but because it explained more consistently. That pattern continues. At this point, Another intuition often surfaces the idea that if something cannot be observed directly, it is less real. This intuition works well in daily life. We trust what we can see and touch, but physics long ago outgrew that constraint. Atoms were accepted before they were imaged. Neutrinos were accepted before they were detected. Gravitational waves were accepted before they were measured. Reality is not defined by visibility. It is defined by explanatory necessity and predictive success. The early universe is real not because we see it, but because models that include it explain what we do see far better than models that do not. James Webb strengthens this necessity. Its observations are more difficult to explain without an early hot, dense phase than with one. So rather than undermining the Big Bang, Webb reinforces the conditions that require it. Now let's pause again and rest. We understand that cosmology reconstructs history backward. We understand that observation constrains models, not replaces them. We understand that the Big Bang is a regime inferred from consistency, not a witnessed event. We understand that frameworks evolve without collapsing, and we understand that lack of direct observation does not imply lack of reality. This prepares us for the final major adjustment before scale reaches its limit, the difference between origin and explanation. They are often treated as the same. They are not. Explaining how the universe behaves does not require explaining why it exists. Cosmology addresses the former. The latter lies outside its scope not because it is forbidden, but because it is structurally inaccessible. Confusing these two creates false expectations and unnecessary tension. As we continue, we will return carefully to the opening claim not to overturn it dramatically, but to place it precisely where it belongs, stripped of excess meaning and stabilized by context. The moment we separate origin from explanation, the pressure to resolve everything at once begins to ease. We no longer need a single answer that satisfies curiosity, intuition, and language simultaneously. Each has different tolerances. Cosmology explains behavior. It explains how the universe expands, cools, and structures itself over time. It does not explain why there is a universe rather than nothing. That question is not deferred. It is orthogonal. This distinction matters because much of the discomfort around older than the Big Bang comes from smuggling existential expectations into a physical framework that was never designed to carry them. Once those expectations are removed, what remains is remarkably stable. The Big Bang model tells us that the observable universe emerged from a hot, dense state and has been expanding and cooling ever since. It does not assert that this state was the absolute beginning of all existence. It does not deny the possibility of prior phases. It simply does not require them. This restraint is often misinterpreted as evasion. In reality, it is discipline. Physics only commits to what can be constrained. Beyond that, it maps possibilities without selecting among them prematurely. James Webb's observations live entirely within this disciplined space. They do not demand answers about ultimate origin. They demand better accounting of early conditions. Another intuition tends to interfere here, the belief that if something is not required by current explanations, it must be irrelevant. In physics, irrelevance is contextual. A process may be irrelevant to one question and essential to another. Pre-Big Bang scenarios may be irrelevant to galaxy formation, while remaining relevant to questions about quantum gravity. So when cosmologists say that early universe physics does not require a before, they are not closing the door. They are keeping the model minimal. Minimal models are powerful because they reduce assumptions. They survive longer. They are easier to falsify. The Big Bang model has survived not because it answers everything, but because it answers what it claims to answer exceptionally well. James Webb strengthens that position by tightening constraints on early structure formation. It narrows the space of viable histories without forcing a leap into speculation. This is how science progresses at scale by compression, not expansion. Each new observation reduces ambiguity. It does not explode it. Now consider how language amplifies confusion. Phrases like the beginning of time and before the universe are metaphors. They are not equations. They are attempts to gesture toward limits of description using everyday grammar. When these phrases are taken literally, they generate paradox. When they are translated back into technical meaning, the paradox dissolves. Beginning of time means the earliest regime our models currently describe. Before the universe means outside the domain of this framework. Neither phrase asserts impossibility, neither asserts existence. This translation is rarely made explicit outside technical contexts, which leaves room for misinterpretation. James Webb headlines exploit that gap not maliciously, but inevitably. Dramatic phrasing travels farther than precise explanation. So when you hear that something appears older than the Big Bang, what is actually being said is that early structures formed faster, earlier, or more efficiently than some simplified expectations assumed. That is not a threat to cosmology, it is an update to it. Now, let's revisit the opening intuition gently. We began with the idea of a clean starting line, a moment where everything begins. That idea is psychologically satisfying because it mirrors human experience, birthdays, anniversaries, milestones. The universe does not offer that kind of marker. Instead, it offers overlapping regimes, transitions rather than instants, phases rather than events. The Big Bang marks one such transition, the earliest one we can currently describe with confidence. It is not a wall, it is a horizon. Horizons are not edges of reality, they are edges of access. This distinction is subtle, but once internalized, it stabilizes understanding across scale. Now, another intuition often emerges at this stage, the idea that acknowledging limits diminishes knowledge. In reality, the opposite is true. Knowing where explanations stop is part of knowing what they are. Boundaries give structure. They prevent overreach. They protect coherence. Cosmology is unusually explicit about its boundaries because it operates at the limits of observation and theory simultaneously. James Webb does not blur those boundaries, it sharpens them. It tells us how early stars formed. It tells us how quickly galaxies assembled. It tells us what kinds of structures existed at early times. It does not tell us what preceded the earliest describable regime. It does not need to. At this depth, we can pause one more time. We understand that cosmology explains behavior, not existence. We understand that minimal models are a strength, not a weakness. We understand that language often overreaches technical meaning. We understand that the Big Bang is a horizon, not a wall, and we understand that Webb refines early history without demanding ultimate answers. This sets the stage for the final descent, not into mystery but into resolution. We will return to the claim in the title not to dismiss it, but to translate it fully, to strip away what it implies incorrectly and retain what it reveals correctly. At this point, the phrase in the title can finally be handled without distortion. James Webb just detected something older than the Big Bang sounds like a challenge to the entire structure we've built. It feels like a violation of order, something out of place. But now, with the layers separated and intuition recalibrated, the phrase changes shape. Nothing has been detected that predates the earliest describable regime of the universe. Nothing has been observed outside the framework of cosmic expansion. Nothing has been seen that requires time to run backward or physics to be abandoned. What has been detected is something older than a simplified story. The story where galaxies must wait politely. The story where complexity unfolds slowly and uniformly. The story where early automatically means simple. Those stories were never physical laws. They were cognitive shortcuts. James Webb exposes where those shortcuts break. To see this clearly, we need to distinguish between two meanings of old. One is chronological, the other is developmental. Chronological age refers to position on a global timeline. Developmental age refers to internal state, how many processes have already occurred. A person can be chronologically young and developmentally advanced. a system can be early in time and late in structure. Cosmic systems behave the same way. When Webb observes galaxies that appear chemically mature at high redshift, it is revealing developmental maturity, not chronological impossibility. Those galaxies have undergone rapid internal evolution within a short cosmic interval. This distinction dissolves the paradox entirely. The Big Bang sets a lower bound on chronological age within the observable universe. It does not constrain developmental pathways beyond what physics allows. Gravity, cooling, feedback, and dark matter allow extremely fast development under early conditions. Webb is detecting systems that took advantage of those conditions efficiently. Now consider why this felt so counterintuitive. Our expectations were shaped by models that emphasized average behavior. Averages are useful, but they hide extremes. When we imagine early cosmic history, we unconsciously picture the median case, not the fastest. James Webb is not sampling the median, it is sampling the detectable extremes. This matters because extremes arrive first. The earliest stars are the most massive, the earliest galaxies are the most active, the earliest detectable systems are the brightest. These systems dominate early observations not because they are typical, but because they are visible. Once this is internalized, the phrase older than the Big Bang collapses into a more accurate translation, more developed, earlier than expected. That translation lacks drama, it gains precision. Now, let's slow the scale again and rest inside what this actually means for our understanding of the universe. It means the universe did not idle at the beginning. It means structure formation was aggressive where conditions allowed. It means our intuition underestimated the efficiency of early processes. It does not mean time behaved differently. It does not mean causality was violated. It does not mean physics was bypassed. The adjustment is internal, not external. James Webb is forcing us to let go of a quiet bias, the belief that simplicity is the natural default. In many physical systems, simplicity is fragile. It exists briefly, if at all. Once gradients appear, evolution accelerates. The early universe was filled with gradients, tiny density variations, temperature differences, quantum fluctuations stretched to macroscopic scales. Those variations did not wait, they amplified. From that amplification, complexity followed not reluctantly but inevitably. This realization stabilizes something deeper than any single observation. It stabilizes how we should expect the universe to behave when pushed far from equilibrium. Far from equilibrium systems do not evolve gently, they reorganize rapidly. The early universe was the ultimate far from equilibrium system. So when Webb shows us early galaxies that look unexpectedly organized, the correct response is not surprise, it is recalibration. Now, there is one final intuition that tends to linger, the idea that if something challenges our expectations, it must be overturning what we know. This is rarely true in mature sciences. In mature sciences, revolutions are rare, refinements are constant. The Big Bang model is a mature framework. It has absorbed decades of data across independent domains. It is not brittle. James Webb does not crack it, it loads it. It adds pressure in specific places, early star formation rates, feedback efficiency, initial mass functions. Those pressures improve resolution, they sharpen predictions. This is what healthy science looks like at scale. At this depth we can pause again. We understand that older can mean developmentally advanced, not chronologically prior. We understand that Webb detects extremes, not averages. We understand that early complexity reflects efficient physics, not anomaly. We understand that the Big Bang constrains time, not development. And we understand that expectation failure does not equal model failure. What remains now is not explanation, but return. Return to the familiar world, return to the idea we started with, not to discard it, but to hold it differently. The universe still has a history, it still has early phases, It still expands from a hot, dense state. We simply understand now that its early behaviour was more active, more diverse, and more efficient than our intuition allowed. In the final stretch, we will bring this understanding back to the opening frame, not to close the book, but to place it back on the shelf, labelled correctly, with its contents intact. With the pressure released, what remains is clarity rather than resolution. The universe does not simplify at the end of explanation, it stabilizes. We can now look back at the path we've taken without retracing it explicitly, because the structure holds on its own. We began with a familiar idea, a beginning that feels clean, punctual, and singular. That idea did not collapse because it was foolish. It collapsed because it was underspecified. It worked at human scale and failed quietly at cosmic scale. What replaced it is not a competing story, but a different frame. The universe did not begin in the way stories begin. It entered a describable regime. From that regime, everything we observe followed lawfully, but not uniformly. This matters because it restores something intuition often loses under pressure: proportionality. Early does not mean simple, later does not mean complex, young does not mean undeveloped. These associations are local habits, not universal rules. Once this is internalized, the universe stops feeling like it is violating expectations and starts behaving exactly as constrained systems do under extreme conditions. Another quiet correction settles in here: the idea that understanding should feel satisfying. At small scales, understanding often arrives with closure. You solve a problem, you finish a task, the uncertainty ends. At cosmic scales, understanding feels different. It feels open, but stable. The boundaries are visible. The interior is coherent. The edges are acknowledged rather than filled. This is not incompleteness. It is structural honesty. James Webb operates comfortably inside this kind of understanding. It does not aim to finish cosmology. It aims to refine it. Its discoveries feel unsettling only if we expect finality. If we expect convergence toward a single, finished picture. But cosmology converges toward constraint, not completion. Each observation narrows what is possible. It does not collapse possibility to a point. This is why we don't know appears naturally and legitimately in this field, not as a placeholder for ignorance, but as a marker of where explanation currently ends. We don't know does not mean anything could be true. It means this is the boundary defined by current constraints. Beyond that boundary, speculation exists, but it is labelled, separated, and disciplined. James Webb has not moved that boundary backward, it has moved it sideways. It has increased resolution within the known domain rather than extending the domain itself. This distinction is easy to miss because both feel like progress. But they are different kinds of progress. Resolution reveals texture, extension reveals new territory. Webb primarily does the former. It reveals how rapidly stars ignited, how efficiently galaxies assembled, how uneven early structure formation was. These details deepen the picture without changing its frame. Now consider what this does to the opening claim when held properly. Older than the Big Bang no longer sounds provocative, it sounds incoherent. Not because nothing interesting happened early, but because the phrase misaligns categories. It mixes developmental state with chronological order. It confuses model boundaries with physical events. Once that confusion is removed, the drama evaporates and something more durable remains. We are left with a universe that behaves consistently across scales, even when our intuition does not. That consistency is not trivial, it is earned. It emerges from independent measurements converging on shared constraints, expansion rates, elemental abundances, background radiation, structure distributions, stellar physics. James Webb adds another layer of convergence. It does not destabilize the picture. It strengthens it by forcing internal coherence at higher resolution. At this stage, one final intuition often tries to assert itself: the desire for a definitive endpoint. a final sentence that declares understanding complete. Cosmology does not offer that. What it offers instead is a stable platform from which future refinements can proceed without collapse. This is why the ending of a cosmological explanation rarely feels like an ending. It feels like a pause. The universe continues to evolve, instruments improve, models adjust, boundaries shift incrementally. Understanding grows not by replacement, but by accretion. This may feel unsatisfying if we expect answers to behave like stories, but it is deeply satisfying if we accept them as structures. Now we can rest again inside what holds. We understand why early galaxies appear mature. We understand why that does not violate cosmic timelines. We understand why the Big Bang is a boundary of description, not a birthday. We understand why detection favors extremes. We understand why new data refines rather than overturns. And we understand where explanation ends cleanly, honestly, without mystery inflation. What remains is not a gap to be filled, but a frame to be carried. As we approach the end, we do not need to introduce anything new. We only need to return to where we started, now with intuition rebuilt rather than challenged. The universe still has a past. It still expanded from a hotter, denser state. It still formed structure through gravity and time. James Webb has not changed that. It has simply shown us that the early universe was more capable than we assumed and that our assumptions, not reality, needed revision. Tonight, we began with something that felt settled, the idea of a beginning, a clean starting point where the universe arrives fully formed into time and everything else follows. That idea was familiar, it was useful, and it was incomplete. Nothing we have walked through requires abandoning the universe we thought we knew. It requires holding it with a different kind of precision. The universe still has an early phase. It still expands. It still cools. It still forms structure through gravity acting on matter over time. What has changed is not the story, but the scale at which we are able to listen to it. James Webb did not uncover something forbidden. It did not peer behind a curtain that physics had declared closed. It did not overturn the framework that describes cosmic history. It did something quieter. It forced us to notice where our intuition had been substituting narrative for mechanism. We assumed early meant simple. We assumed development required patience. We assumed complexity needed time to accumulate slowly. Those assumptions came from our experience, not from physics. The early universe did not wait. Under extreme density and energy, it acted decisively. Gravity amplified small differences. Dark matter shaped invisible scaffolds. Gas cooled, collapsed, ignited, and recycled efficiently. James Webb showed us the results of that efficiency. Not earlier than time, not outside expansion, not before the universe. Earlier than we expected because our expectations were conservative. That distinction matters because it preserves stability. Nothing we now understand forces us into speculation. Nothing demands rewriting causality. Nothing requires new physics to explain what has been observed so far. The Big Bang remains what it always was, a description of an early, hot, dense regime inferred from converging evidence, a boundary of applicability, not a moment of creation. That boundary has not moved. What has moved is our comfort with what happens close to it. We are now better at holding multiple truths at once. That early cosmic history was brief and intense. That structure can emerge rapidly under the right conditions. That observation samples extremes before averages. That models improve by tightening, not by collapsing. This is what progress looks like at extreme scale. It does not feel like revelation. It feels like alignment. Alignment between observation and expectation. Alignment between model and constraint. Alignment between what we see and what physics allows. The discomfort we felt along the way was not a warning signal. It was the sensation of intuition being asked to operate outside its native range. Now that recalibration has occurred, the picture holds. The universe no longer feels rushed. Early galaxies no longer feel out of place. The Big Bang no longer feels threatened. Everything sits where it should, once we stop demanding that cosmic history resemble human timelines. And this is where we end not with answers sealed, but with understanding stabilized. This is the reality we live in. A universe that began in conditions we can describe, evolved through processes we can constrain, and continues to reveal itself through instruments that extend our reach without breaking our frameworks. We understand it better now, and the work continues.